Have you ever just stopped and wondered how everything, well, works? How the same fundamental rules can build a tiny atom, a massive star, and even you? Well, in this explainer, we're going to go on a high-speed tour through the core ideas of chemistry, physics, and biology to connect all those dots. So let's get right to it. Here's our game plan. We'll kick things off with chemistry's chemical code, then see how those building blocks actually behave with the forces of physics. After that, we'll jump into biology to see how they create the blueprint of life. And finally, we'll pull it all together to see the big picture. All right, let's dive right in. First up, chemistry. This is the fundamental code, the instruction manual that dictates how every single thing in our universe is put together. Okay, so we start with a law that's like universal, the conservation of mass. It's a really simple but incredibly profound idea. In any chemical reaction, the total mass of whatever you start with is exactly the same as the total mass you end up with. You can't create it, you can't destroy it, you just rearrange it. That's it. Building on that, we've got the law of definite proportions. This basically means that a compound, let's take water for example, is always made of the exact same stuff in the exact same ratio. So no matter where you find H2O in the entire universe, its hydrogen to oxygen mass ratio is always locked in at 1:8. It's totally reliable. So these laws led this guy, John Dalton, to a truly revolutionary idea, his atomic theory. He was the one who proposed that all matter is made of these tiny, indivisible particles called atoms. He figured they combine in simple whole number ratios and that chemical reactions are just the atoms getting shuffled around. I mean, this was a complete game changer for how we understand matter. And all this talk about atoms, of course, brings up a really basic question. What exactly is a molecule anyway? It's actually pretty simple. A molecule is just what you get when two or more atoms link up through chemical bonds. The oxygen we're all breathing right now, O2, that's a molecule. The water we drink, H2O, is a molecule. It's just the next step up in organization from a single atom. Now, here's the thing. Atoms and molecules are unbelievably small, so chemists needed a practical way to count them. And what they came up with was the mole, which stands for this absolutely gigantic number you see on the screen. But listen, don't let that number scare you. A mole is really just a counting unit. Think about it like this. A dozen always means 12, right? Well, for a chemist, a mole just means 6.022 times 10 to the 23rd particles. It's their version of a dozen, just a lot bigger. It's the standard way to measure stuff in chemistry. Okay, so now we have our chemical building blocks. Let's switch gears to physics and try to understand the forces that tell them how to act. We're going to start with two forces we deal with every single day, pressure and buoyancy. Let's start with pressure. You see, pressure isn't just about how much force you're using. What's just as important is the area you're applying it over. It turns out that even a tiny bit of force, if you focus it on a really small area, can create a ton of pressure. This relationship is everything. Think about it. If you concentrate a force over a teeny tiny area, like the point of a pen, you generate way more pressure. But if you spread that same force out over a larger area, like the palm of your hand, the effect is so much smaller. And here's the perfect real-world example, a sharp knife. The force from your hand gets focused onto that super thin edge, creating so much pressure that it can slice right through a tomato. A dull knife, well, it has a larger surface area, so it just can't create that same kind of intense cutting pressure. So what about forces and fluids, like water? This brings us to the famous Archimedes principle. It's such an elegant idea. It just says that when you put something in a fluid, it gets pushed up with a force that's equal to the weight of the fluid it moved out of the way. And the results of this one simple principle? They're huge. It's the reason a giant steel ship can float, because it displaces a massive amount of water. It's how submarines can dive and resurface. Heck, it's even used to test the purity of gold. It's a seriously powerful concept. So we've gone from atoms to the forces that boss them around. Now, let's pivot to biology and see how all this stuff comes together to build life itself. We'll start with the body's fundamental building materials, tissues. So if you zoom out and look at the big picture, animal bodies are built from four main types of tissue. You've got epithelial tissue for covering surfaces, connective for support, muscular for movement, and nervous tissue for sending messages. Let's take a closer look at connective tissue because it's incredibly diverse. I mean, check this out. It includes everything from solid bone that gives our skeleton structure to the ligaments that hold those bones together, all the way to blood, which is actually a fluid tissue that's busy transporting materials all over our body. Now, nervous tissue is all about communication. A nerve cell, a neuron, it's basically like a biological wire. It works in 3 simple steps. First, the dendrites receive a signal. Then, the cell body figures out what it means. And finally, the axon shoots that message onward to the next cell. Simple as that. All of these tissues work together to carry out the core processes that actually define what it means to be alive. Things like nutrition to get energy, respiration to actually use that energy, transportation systems to move supplies around, and of course, excretion to get rid of all the waste.
Okay, for our last section, let's zoom all the way out. We've just sprinted through 3 different scientific fields, but the real magic, the really cool part, is seeing how they're not separate at all. They're all deeply connected.
So here's how it all clicks together. Chemistry gives us the alphabet of the universe, the atoms and molecules. Physics writes the grammar, the fundamental forces and laws that decide how that alphabet can be combined. And biology? Biology is the epic story that's written with those letters and rules, all the complex, living things that emerge. And that leaves us with one final, pretty amazing question to chew on. We've just looked at a set of beautifully simple, elegant rules. So how do these fundamental principles combine in just the right way to create everything we see, from a simple rock, to a distant star, to life itself?